Hopefully the audio's back now. Hello, 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 hello. Okay, thank you. Jake?
I'll put a grading for the lab coming.
Yeah. I'm aware there's a big issue there. We'll put it like that. I will check. We're suffering from the fact that Rohit has a PhD proposal defense coming up here shortly. Other questions? So that, in case you were wondering what that question was, that was how's the grading for the lab coming in? Yeah, it's just a subject we don't want to talk about.
This has probably been a pretty long issue, but move on. But like, is there any way we can get like 2 more screens up in that lab, just for like 2 of the computers? Because damn, it seems really like, you know how like.
Wait. So all the computers are dual monitor systems, right? Okay. All right. So the lab up there has it's supposed to be stocked with every computer has dual monitors, but they are in the process of replacing the computers. So Justin's rebuilding the systems. He may have stolen the monitors.
The monitors are in the Linux labs of the competition. Yeah.
Oh, it's your fault. Okay. We will. Does the dual monitor thing actually help?
Yeah.
All right, I'll talk to him about it. Okay? Just make sure you sit at the right station up there that has the dual monitors in. I mean, early bird gets the worm. Okay, other questions? It's exam review day, so I don't present anything. I'm not going to say anything unless you guys ask.
So is the midterm mainly on the labs?
Is the midterm mainly on the labs? To the same degree that the midterm has been on the labs in prior years and in the prior exam in this class. So I'd say, oh yeah.
Do you need anything in particular from the book?
You need anything in particular from the book? Well, anything's fair game. So the format of the exam will be just like the format of the practice exams you've seen on the screen. Even though this is a take-home and those were in class, the format of the exam will be about the same. I'll have a page of Q&A where those are, may be answered from the labs, may be answered from stuff that's in the book. But I doubt that I'll spring anything on you that I haven't talked about or referenced at least in lecture. So if it's in the book, then it's stuff that I've perhaps quickly, but at least touched on when I talked about in lecture.
I mean, one of the problems is optimizing the context switch code for cooperative.
Yep.
Because we know how to do it in the last lab, but not so much with cooperative.
Okay. So, Fall 2007 exam has a problem where it says, please optimize the context switch code for cooperative context switching. So this is the problem here. Design and implement a new context switch code which is optimized to implement only cooperative context switching. Your implementation should be as space efficient as possible, pushing only those registers which are necessary. Your context switch code should work correctly when called from a variety of processes which are implemented in C and compiled using our cross compiler. Your context switch code does not need to work correctly for preemptive scheduling. So here's the original context switch code. This is the one that you've been using from Lab 6 and on. What should you do to it in order to make it work for just cooperative context switching? Why would we want to do this? Yeah, Tony.
I tried looking for collar save and collie save. They haven't listed any notes. They listed. We were actually.
I don't recall ever actually telling you which registers in ARM were caller save and which ones were callee save.
You mentioned it.
I mentioned that there are caller save and callee save registers, and I recall asking you in Lab 5 to figure out which ones they are.
Oh. We got that one back yet from the grader.
Ooh.
The point about whether or not you get it back from the grader, we tend to grade labs kind of easy on them. So there's a lot of participation points that you get. So if I can tell on the labs, and this is how I've instructed him to grade Lab 5, so if I can tell on the lab that you had a thorough process and you justified your answers, you're going to get credit. Or in other words, if you put the wrong answer down, he may not tell you. We try to, but I can't point out every wrong thing that you do on the lab. It's not that I'm trying to be obfuscated. You know, in a situation like that, you know, anything that's significant and important, we're going to point out. But there's things that are going to slip through. Anybody have any questions? Mitch?
So is this the same, sorry to stray, but is this the same as the first exam where it's open everything besides internet and gaming?
Yeah, the exam will be open book, open notes, closed humans, closed internet. Well, open you. I suppose you're a human. Some people don't think I am. Tony, do you have any particular questions about this question that you'd like to ask me in the middle of class?
No.
Such as, what are the caller save and callee save registers for ARM?
I was going to say that we looked through the user's manual, but it didn't really specify whether they were or not. So I wanted to verify.
Let me clarify one other issue. Even if you get a grade back from the grader and it says you got full credit on the lab and that maybe or maybe not points out what you did correctly or doesn't point out what you did correctly, I will discuss lab solutions with you. Okay? I am happy to cuss and discuss that. I'll go over your code with you. I'll set up approaches with you. I'm not trying to hide that information from you. Okay? So, but again, there's a lot of stuff in each lab. You guys know that. We don't have time to debug every nuance of your code. So there's going to be things that you do erroneously that's going to slip through the grading. Yes? That is a fantastic question. What are the caller and callee save registers of the ARM architecture? Somebody tell me, what do you think? What? R0 through R3, caller or callee? Okay, all right. Who doesn't want to vote? Okay, all right. You two are excused. How many of you vote caller save? How many of y'all vote callee save? How many of y'all are chickens? Mitch and Stephen, because they raised their hands. Okay, what makes a register a caller save register?
Caller saved it before.
Who's got to save it? The caller. Who's the caller? The person, the code. So we are treating C functions as if they were people, you know, and it's kind of clunky, but this is what we do. So if you've got a C function, every C function gets called. Every C function that you write gets called. Does every C function call other functions? Not necessarily. A C function can act in the role of caller, and it can act in the role of callee. Okay? Every C function acts in the role of callee at some point because every C function gets called. It is the target of a call. It will only play the role of a caller if it calls another function. Okay? So if we're talking about caller save and callee save registers, if you put a piece of data into a register and you expect it to be preserved across a function call, the idea is I'm going to call a function. I've got data that I'm going to put into a register. If I want it to be preserved across that register, the idea behind caller save and callee save registers is the function that I call going to whack the value in there? Can I assume that it's going to whack the value or not? Okay? So if I want to preserve a value across a function call, I'm the caller. Should I put the value that I want preserved into a caller save register or a callee save register? If I have a value that I put into a caller save register, who has to save it? The caller, that's me. So in other words, I put it in a caller save register. If I'm going to call a function, I got to take it out of that register and put it on the stack. So I'm trying to avoid having to put it on the stack. I want it to be preserved. I want it to sit in that register, live in that register, and stay in that register until the call finishes. So I put it into a register that is not a caller save register because I assume every caller save register gets whacked. Okay? So there are caller save registers and callee save registers. So if a caller wants to preserve a value across a function call without saving it to the stack, you should put it in a callee save register. That way it delegates the responsibility of saving it to the callee. The callee can decide whether or not it wants to whack the callee save registers or not. So there are times where you whack the callee save register, and if you do, you got to save it, whack it, use it, do whatever, then restore it when you're done, because you assume that your caller has values in that register that have to be preserved across the function call. Similarly, if you are the callee and you want to use a register, I want to use the caller save registers, because the caller save registers are registers that have had values placed in them, but we assume that it's okay for any function, once it gets called, to whack the caller save registers. Because if the caller has any valid values in them, the caller had to push them onto the stack, and he will be responsible for restoring those values before he uses them. So a callee wants to use caller save registers. A caller wants to use callee save registers. The downside of when a caller wants to use a callee save register, he writes a value in a callee save register, but every caller is also a callee. Okay? So if a caller wants to have a value preserved in a register across a function call by writing it into a callee save register, well, he's still got to save the callee save register because of the fact that the caller is also a callee. Kind of a darned if you do, darned if you don't principle. But the whole point is that there are certain registers that when you call a function, we assume that that function will whack them. And so I don't assume values are preserved across that function call. So caller save registers are the set of registers that get whacked when I call a function. So what does our cross compiler output when it produces assembly code for a particular C function? You remember when you generate assembly code, what are the first statements that it outputs? You compile hello world. Optimization's turned off. You should have done this about a gazillion times. Remember, it moves SP into IP, and then it has an STMFD, and it saves 4 registers. Which 4 registers does it save? SP, IP, LR, PC. Turn optimizations on. Does it save those registers? It does not necessarily blanket save them all. It'll save them if it needs to save them. So when your optimizer's turned on, for example, if you have the link register gets whacked every time you call a function. So the optimizer, when it's turned off, the compiler, without optimizations on, will just assume that every function that it compiles may end up whacking the link register, because it may end up it may end up calling a function. And not only that, but it's going to use an STMFD to store it, then it'll use the LDMFD to grab the value that it stores in the link register and copy that into the PC, doing a return. So if you have the optimizer turned on and you compile a function that does not call another function, there's no need to store the link register because the value will be preserved in the link register itself throughout the body of the function. So therefore, you can just keep from having to push it onto the stack and pop it back off. So there are times where you can avoid pushing and popping all those, the LR, the FPIPPC and LRPC, those four guys. So are those guys call or save or call eSave registers? How about the frame pointer? Call or save or call eSave? Call or save. So before you call a function, do you push the frame pointer onto the stack? No, you don't. When do you use the frame pointer? When you reference local variables. When you establish the frame pointer to where it points at your stack frame. When you enter your function, right? When you begin, regardless of whether you're calling a function or not. So this is at call E time. So a function gets called, and the first thing that it does is it saves its stack pointer, and it saves the old value of the frame pointer, and then it points the frame pointer register at its stack frame. One of the last things that it does is it restores the frame pointer of the calling function. So, call E save or call R save? Call E saves it. Call E restores it. The caller can assume that the frame pointer register will retain its value across a function call because the call E saves it and restores it. How about the IP register? Call or save or call E save? IP register is the intra-procedural something or other register. It's kind of both and kind of neither. Because the first instruction that the compiler emits in unoptimized assembly is it moves the stack pointer into IP. So it overwrites the value without saving it. So that would seem to indicate that it's a call or save register. So now the next question is, what's the first thing that a call... So if a callee can whack it, that means it's the caller's responsibility. But does the caller save IP before it calls a function? No. This is just assumed to be a scratch memory location that anybody can whack anytime that they want to. We use it to hold what the stack pointer is and push that onto the stack so that we can use SP in addressing the STMFD and LDMFD instructions, and we can use the value of IP as a temporary location to hold the stack pointer. In our context switch code, we could have designed it to use IP for that similar reason. So, how you determine what are the caller save and call E-save registers is an artifact of Lab 5. And you should have figured this out in Lab 5. And, okay, so how about R0 through R3? What are the roles of R0 through R3? Passing parameters. Caller save or call E-save? Caller save? Okay. Can you prove to yourself that R4 is or is not caller save? How would you go about doing that? What type of experiment do you conduct to determine whether or not R4 is caller save or call E-save? So by adding more parameters to a function, you can determine whether or not R4 gets used to pass parameters to a function. That's not necessarily what we're after. What you have to have is you have to force your compiler to allocate variables in your function that you're using, and it has to make use of R4. And then you have to see whether or not it saves its value and then restores it across a function call. Okay? So you have to have a lot of local variables, and you have to use them before a function call and after a function call. And you have to make the compiler optimize so that it makes use of R4, R5, R6, and you've got to see whether or not it preserves those values by storing them on the stack first before it whacks them. If it just whacks them without storing them on the stack first, those are caller save registers. If it whacks them after storing them on the stack, they're called e-save registers. Mitch?
So usually, it would just allocate space on the stack for all your local variables. So to force a few registers, you just turn on optimization.
So the unoptimized, so the question is, how do you make it use registers instead of stack space for local variables? Even unoptimized compiler output tries to use registers where it can. But if you turn the optimizer on, then it'll even more so try not to use stack space for local variables. What does caller save and call e-save registers have to do with this problem? Tony?
Context switch is called. You don't really need to save any registers that were saved by the caller.
Okay, so the point is what we're trying to do is eliminate the saving of registers twice. Remember how we did this with preemptive scheduling, where we let ISRs save registers once, and we don't want to save it again inside context switch. Well, if we have caller save registers and call e-save registers, what we can assume is that any value that gets passed, or any value that gets stored in a caller save register, CS is a function that gets called. That means that the caller of CS has to assume that CS is going to overwrite the contents of the first four registers because they're defined as caller save. Okay, so CS can whack those values, and the caller has to assume that it's going to whack those values. So if it wants to have values that it preserves in R0, R1, R2, and R3, if it wants those values to be preserved in those registers across a function call, the caller will save them. Or in other words, if there's something that we need to have inside R0, R1, R2, and R3, schedule the next process, if it wants to have those values kicking around after the call to CS, it will save them. We don't have to save them, by virtue of the fact that they are caller save registers. So no valid values will be held in R0, R1, R2, and R3 from the perspective of caller save versus call e-save. Okay? There may be a gotcha with that. And I'm not going to tell you what it is. Unless, of course, you come and talk to me.
How do we do that on the weekend?
I would suggest talking to me about this problem before the weekend. Mitch?
So you're saying to optimize this, then that you would just not push?
Don't push caller save registers. Push your call e-save registers. Don't push your caller save registers. Okay?
How would you optimize this?
Well, if you're doing, do you need to mode switch if you are doing cooperative context switching? Are you sure? That would be a question you've got to ask yourself. So what you should do is then look into the whole business of mode switching. Do you need to mode switch? And I would suggest you probably don't need to do as much funky mode switching. You need to look into the reason of why we pushed the pointer to self on top of the stack. And do we need to do that if we're only doing cooperative context switching? And throw out as many of these instructions as you can. So optimize it for both space and time. So use as little stack space as possible. You know, you have to have stack space. You have to push your registers that you need to save onto the stack. So there's no way around that. But there are some registers you don't need to save. There are, and then on top of that, you don't necessarily need to save the pointer to self because we use that due to the need to restore the original IRQ stack pointer to the original IRQ stack. Okay?
So you say don't push the registers, like all the registers? Well, I'm just trying to digest here.
Okay.
But, so you say don't push the call E registers, so there's 4 that you don't need to push on.
Don't push the caller save registers.
Right.
Okay?
So, in this, it uses
With
R1,
perhaps a gotcha.
R1, R2, R3. So we know we need to use at least 3 registers.
Okay, so caller save registers. We've identified R0, R1, R2, and R3 as caller save registers. Callee save registers we do need to save.
You're forced to save all of them, even though you don't use them.
We don't use them in CS, but the point is that you push them onto the stack inside CS because maybe the process that you're interrupting did use those registers and they did have values in them.
And they're in charge of deciding what to throw out.
Mm-hmm. So we assume that those values those registers preserve their values across function calls. And then, so we have to preserve them when we push all the state onto the stack because we're going to swap in a process that potentially could overwrite the contents of those registers. So if we don't preserve them, then the state of the process that we're swapping out is going to get messed up. And we'll start doing funky things like you guys saw in your lab. Okay, have I sufficiently confused the tar out of everybody?
So, like in this question, cooperative context switching, so can we exclude the mode change from, to make sure it's in cooperative mode? No.
Okay, I'm going to hedge a little bit just because I can't remember for sure, but I think so. Okay, from what I remember, yeah, you can exclude the mode switch.
If it's going to be cooperative, then we can just...
There is no need to necessarily look at IRQ mode, anything, if you're just doing cooperative stuff. But if you remember, I gave you 2 lectures on context switching. The first one where I talked about context switching in general, and I gave you assembly code for context switching, and then I talked about the truth, the whole truth, and nothing but the truth. Remember that second lecture where I introduced the whole nasty ISRs and expanded the context switch? The first version of context switching that I gave you worked for preemptive to preemptive switches and cooperative to cooperative switches, but not mixed. So you could go back to that context switch and compare it to this one and see what was missing and what was added, and arguably you can throw out everything that was added. Arguably you could start with that context switch and optimize it further. Okay?
Okay, this might be a dumb question, but I'm going to ask you.
Okay?
If I don't push on R1, R0, R1, R2, and R3 because they're caller state registers, then I can't use them in context switch code, correct?
Okay, so if you don't push them on, it's totally fine. So if you don't push R0, R1, R2, and R3 inside here, you know, that is a very good question. Does that mean you can't use them inside context switch? No. You can go ahead and overwrite them. You don't have to save their values at all. The reason why is because they're caller save registers. Whoever called you, if they have a value in there that they assume should stay in there, it's their responsibility to push that onto the stack. So the caller has to assume that R0, R1, R2, and R3 are going to get overwritten. So yeah, you can totally use them. You can even use them without pushing them and restoring them. So most of you have a look on your face of holy freaking cow. And this was an in-class exam question. Okay. So basically this question said modify your CS, then draw stack frames, then modify all the rest of the supporting code to make it all consistent and work right. And yeah, that was an in-class exam question. I would have expected you guys to be able to do similar things like this. Mitch?
What all is the CPSR used for and stuff?
Okay, the CPSR, what is it used for? CPSR plays several roles, but it holds the whole the processor state with respect to certain things. There's a bit in the CPSR that you can toggle that says, do you want to run in thumb mode or not? So ARM supports a 16-bit instruction, instruction set that's a subset of the 32-bit instruction set. So you can tell it, you can toggle the thumb bit, and it'll configure itself to start running 16-bit code instead of 32-bit code. That would be bad. that would make your program mess up all kinds of bad ways, in all kinds of bad ways. But if you're developing a 16-bit application, you can usually save on code space and have the program assembled to a smaller footprint. The equivalent of the condition codes for x86, ARM has similar condition code, and they're stored in the CPSR. The mode of the processor is controlled by a few bits in the CPSR. There's several other bit fields in there that aren't necessarily relevant to what we're doing, but that's basically the things that... And there's a bit in there that controls whether or not IRQ interrupts are enabled, or whether or not FIQ interrupts are enabled. So
when we optimize it, we still need to save it because there could be condition goes.
So should you have to save the CPSR? Yeah, absolutely. You have to save the condition code. You have to save the CPSR because of the fact that it's got the condition codes, and the behavior of the program is going to depend on having those condition codes set correctly. Not only that, but you have to remember what mode the processor is in. You have to remember whether or not interrupts were enabled or disabled at the time. So yeah, you've got to save CPSR.
What are the other CPSRs there?
So all the things that you're seeing CPSR on there, all of that's mode switching. Except for the last one where, so the first one that you're seeing is this guy's where it's saving the interrupted processes or the swapped out process of CPSR. The last one is where you're restoring the swapped in process of CPSR. Everything in the middle is mode switching. And that one might be a mode switch too. The last one. Okay? Other questions? Derek?
About semaphores, strong semaphores.
Strong semaphores?
When you do when you're doing a block move to ready queue, do you have to call a context switch?
A block move to ready queue.
When you're moving it from the block queue to the ready queue.
Move block to ready.
Yeah.
Okay.
So do you have to call a context switch?
When you implement move block to ready, do you have to call a context switch? No, you don't. You should call your scheduler.
So, like, schedule next process.
You should call schedule next process. What you should do is pull the guy with highest priority off, or do a FIFO remove from S arrow blocked queue, and then a FIFO insert of that process to ready queue, and then call your scheduler. And the reason why is because the guy you pop off the ready queue may not have higher priority than the calling process. So you want the highest priority ready process to run. So if you pop off a guy from the semaphore block queue that has lower priority than you don't want to switch to him, because otherwise you've got a priority inversion where you've just switched to a process that has a lower priority, but yet there is now a process with higher priority that's ready. So don't have priority inversions. So you call the scheduler, and the scheduler determines whether or not there should be a context switch. So should there be a context switch? Maybe. Let the scheduler decide. So in move block to ready, you just pull something off of the block queue, put it onto the ready queue, then call the scheduler.
So let's say the higher priority one off the queue. Does that process start from, because we don't put back the semaphore, we just pass it on to the next process, right?
Mm-hmm.
So I'm confused. I keep thinking, is it going to do another strong P check when you call it next process?
Okay. So the scenario then is let's suppose that the process that was blocked has higher priority than the running process. And let's suppose that we are doing a V in the lower priority process to give the semaphore up, which will cause the semaphore to be transferred to this higher priority process that is blocked waiting for ownership of the semaphore. So what that will do is we will pull that higher priority process off of the semaphore's blocked queue, insert it onto the ready queue, call the scheduler. The scheduler will go through and determine that there is a higher priority process waiting for the CPU, and so it will execute a context switch. So we swap that higher priority process in. What instruction does that higher priority process resume? Where does it go? Where is it at? Does it go back up into a strong P again? Is there any type of looping structures? Does it execute from strong V? Where did it get swapped out? That's the question. Inside strong P? Did you call the scheduler inside strong P? Move to block Q. So move to block Q inside your strong P. Inside your strong P, move to block Q. What it'll do is it'll say, you can't call the scheduler and move to block queue because the scheduler assumes that I'm going to look at the ready queue, and if the current running process has lower priority than somebody on the ready queue, I'm going to take the current running process and put it onto the ready queue and take the higher priority process and make it the running process. That putting the current running process onto the ready queue is bad from the perspective of trying to block a process. If you're blocking a process, like what you're doing inside strong P when you're moving to block queue, you don't want the running process to be put back onto the ready queue. If you put him back onto the ready queue, that means you're still letting him run. You want to make sure that he does not run because he's blocked. Otherwise, you're going to have multiple processes inside your critical section. So what you do at that point is you have to kind of have a hacked version of your scheduler inside move to block queue. And so what you do is you say, you do a FIFO remove and you grab a process from your ready queue. If there's no processes available in your ready queue at that point, what do? There should be something there, but if there's not, what happens? You printf Wizard of Oz, what a world, I'm melting. Okay, this is a deadlock. That's bad. That says that whoever wrote all these processes messed up. Okay? So there had better be something there to run, and if there's not, that's a problem. You grab the highest priority ready process off of the ready queue. It doesn't matter if its priority is greater than or less than the running process because we're blocking the running process. So we take a temporary pointer, point it at the process that process running is point to, and then we point process running at the process we just pulled out of the ready queue. We then change their state values, and we execute a context switch. So we switch from the current running process, and we, before that, we have to actually insert this process running into the semaphore's block queue. So we pull the process out of the ready queue, we put the running process into the block queue, toggle states, switch to the new process. So that's how we block a process. So a process that wants the semaphore gets put on the block queue at that point. It calls CS to get swapped out at that point. So now the question is, when we're swapping it back in and granting it ownership, that process has been waiting on the ready queue. It was swapped out. The last instruction that it executed was in the middle of its context switch. Okay? So its state got saved on the context switch. That context switch was called from move to block queue. So when the process that gets swapped back in after having been blocked, where does it start? Where does it resume execution? Inside context switch that was called from move to block queue. It returns from move to block queue, returns from strong P, and starts executing the critical section. So there is no repeat attempt to grab the semaphore again. We just, as soon as that process returns from its context switch, it owns the semaphore. Okay? So control flow goes from CS, and it returns from move to block queue, owning the semaphore. That'd be a fun test question. Drawing the call stack of swapping in and swapping out a process due to owning a semaphore. Another fun test question could be, well, let's suppose you have a couple of semaphores that you declare. Well, let's suppose you declared pointers to semaphores as global variables. But let's suppose that you don't initialize them. And then you start doing strong P and strong V. And then you block a process. Tell me exactly what happens. Bad things happen, but you should be able to predict it given the fact that you should know where those garbage pointers point. Because if you have an uninitialized global variable, it's in the BSS section, which gets zeroed out. All right? So because of the fact that you can dereference a null pointer and the processor doesn't care, it just starts doing random things, you can write bits to down to add to 0. So you can predict what's going on there. Anyway, that'd make fun test questions. Mitch?
Isn't it a runtime error.
Is not a C runtime library error because the C runtime library doesn't watch the addresses that you're accessing. The memory management unit watches the addresses that you're accessing. And we do have a memory management unit. We've just told it don't care. And where did we do that? We actually inherited that part from Red Boot. There's no code that I've let you see that configures the memory management unit. And you're grateful for that. Other questions? I gave you 3 practice exams with all kinds of problems on it. I've given you actually prior practice exams. I gave you the Fall 2005 and Fall 2006 supplemental exams, right? I didn't give you the supplemental exams? The exam 1 supplemental exams. Okay. One thing you should pay attention to is that, and as I've mentioned before, in prior years that I've taught this class, I taught this Chapter 6 stuff, and that corresponded to exam 1. On this year and last year, the Chapter 6 stuff corresponded to exam 2. Therefore, macro questions about how to implement exceptions fell on exam 1. They didn't fall on our exam 1, so they're fair game for exam 2. Macro questions like these fun things. Implement a bunch of macros that implement the resumption model for exception handling in C++. Catch and throw and resume. This is a fun little tricky one where you got to do a long jump followed by another set jump. You got to have a long jump out to your exception handler, then a long jump from your exception handler back to where you were at. So your raise macro effectively doesn't just call long jump, it calls a set jump, and then it calls a long jump, and you have to have 2 jump buffs. So things like this, macros are fair game. I had another fun one where it was local and remote exception handling, where you had to handle exceptions either locally on the processor, or you could throw an exception to be handled on the host. So where you have a throw local and a throw remote, and a handle local, handle remote, and basically you've got to compile those down to messages that you pass up to the host processor. Fun problem. Anyway, you have to take a look at those. Other questions? You guys are supposed to be asking questions, guys. I mean,
Deer in the headlights.
Deer in the headlights. Oh, how am I going to pass this class? There are no other classes. What do you mean? I have asked on multiple 5780 exams in the past. I think it's this question here. Because I've asked it so many times, I don't know that I'll ask it again. But this is a good problem to practice on, because it really makes you think about how everything all works. So the whole idea is we have processes that never terminate. What happens if a process terminates? Right now your program will crash. What if we want to be able to delete a process? So what I want you to implement is a proc delete. So the proc delete function is kind of like proc create, except for it removes a process from being considered. Okay? So how can you weave this stuff in there so that you have proc delete? The trick is that proc delete should not be explicitly called. It should be implicitly called. So when a process returns, proc delete should automatically get called, and then delete the process, and you switch to whatever next process you should run. Where would it return to? So that's the trick. Where does it return to? A process should return to the function proc delete. So all you have to do is just find the slot in the stack of the process you're creating, put into the return address slot, proc delete. Okay, so work through that one. What else can I tell you about? I will have a short answer section. So make sure you know what static, volatile, and extern are. And there will definitely be another sweet bonus question. It will not be on the Princess Bride. Y'all know that one too well. Eva! Okay? Are we done? Other questions? Have you guys looked at the practice exams?
I got home at midnight and had to get up at 6. Yep.
All right. Now I understand why you're not flooding me with, can you work this one, can you work that one? We postpone the test? You don't want me to postpone the test. Lab 8 is going to be due. Speaking of, Lab 8 is posted.
Yeah, I'll look at it Monday.
2 weeks. So it's due on the 17th of November. All right. Yeah, the Lab 9 will be due as late as I can possibly make it. Okay. This is me. Yes, it's a doozy. Of course it's a doozy. Yes.
So you're gonna make stuff available via email over the weekend then?
I am always. Have you ever sent me an email that I have not responded to? All right, well, let's be done. I'll have my office hours today. I would suggest that you try to take a look at some of these questions and come by and talk to me if you've got questions about them. In particular, if you've got questions about lab solutions, I would be happy to discuss them with you.
How's it going?
It's going pretty well.
I noticed that